Hello, everybody. Welcome to our very first Quantum Speaker Series for 2025. We're excited to have you all here today. My name is Allison Schwartz, and I am the industry co-chair for ATARC's Global Quantum Working Group. And on behalf of myself and Lily Chen and Jason Lee, my government co-chairs, we welcome you here today. We're really excited about our talk today. We welcome Pierre-Luc Dillard-Demers, who is here to talk to us today. Pierre-Luc is a scientist in residence at Quantum City at the University of Calgary, and he is also the founder of the Poly Group, a quantum company that's looking at post-quantum cryptography and blockchain since 2021. And his work is really exciting, focusing on quantum resilience and communications and securing digital assets for quantum computers. As always, we are going to have Pierre-Luc speak today, and then we will hopefully have some time for some Q&A at the end. So if you want to submit in your questions at the bottom in the Q&A button, we'll be happy to take that. But with that, Pierre-Luc, I will turn it over to you.
Thank you, Alison. Thanks all for joining for my talk on Bitcoin as a quantum canary. I guess we can cut the chase, like for those attending the talk. I guess you came here to know like what happens to my Bitcoin on Q day. And I think that's a good reason to talk about this topic. We'll see because there are more cryptocurrencies, blockchain users than people who know about quantum computing. So often when people like the general public will hear about quantum computing, it's actually a question you will get. So what will happen to my Bitcoin, my cryptocurrencies? And it's actually a topic with the subtleties, and like I'm going to try to paint a broad picture of the consequences of like quantum cryptanalysis on cryptocurrencies. And if there's a message I want you to carry after the talk is that if there's like any system for which we will see the impact of like the point where the size of the hardware and the scale of the algorithm meet, it's likely going to be cryptocurrencies for a different set of reasons. And to explain this, so like in like about 20 minutes, I will have to go through a set of like fairly technical topics, and like since the audience background is fairly broad, I'm thinking of building the case by simply explaining like the different technical components, and then building it up to the end to show you like what's the risk factor for blockchains, what can be done to mitigate this risk, and what are the next steps in securing digital assets against quantum computers. So I'll start with like a brief review of elliptic curve cryptography. A lot of people from the quantum side know about factoring, but not about elliptic curve crypto. Then I'll quickly cover the recent results in cryptanalysis. And then I look at the quantum computing roadmap to give an idea of the timelines, and then the impact on cryptocurrencies and how to upgrade them. So elliptic curve crypto. Most people know about factoring. So as a public key system where you can like prove your identity by signing a message, and whose security relies on the difficulty of factoring, which can be broken by quantum computers. But like the same methods can be used for breaking elliptic curve cryptography. And elliptic curve cryptography was invented in the 1980s. Basically, you have some algebraic curve with an equation, and you can define point addition, multiplication on this curve geometrically. And through mathematic, like this translates to finite fields on which you can define cryptographic methods. And specifically on cryptocurrencies, like like Bitcoin, there are really like two main cryptographic primitives. So you often hear about mining, so like where you verify like the validity, like you establish consensus by repeating the same function over and over. This is not really vulnerable to quantum attacks, but your signature, so your ownership, if you want your wallet, is secured by elliptic curve cryptography, and this is the part which is vulnerable. And classically, so like those methods have been tested like for years, and there's a set of challenges called the Sorticon challenges, which kind of benchmark the progress at breaking elliptic curve cryptography, and the size of the keys we're using is 256 bits. And so far, the classical cryptanalysis has only been about to go halfway to about 120 bits. And each time you add 4 classical bits, you double the classical difficulty. So classically, we're still very far from breaking it, but on the quantum side, it's a different story. And so quantum cryptanalysis, I guess everyone here knows Shor, which is Shor algorithm, and from 93, you can take a public key, whether it's RSA or elliptic curve crypto, shove it into your quantum computer, and you can extract the private key. If you have blockchains, it means you can essentially like spend anyone's coins if you can break their keys. And the recently, so like say on the side of cryptanalysis for factoring, there has been recent progress from 2019 by Craig Gidney and Ekera on reducing the number of qubits that you need to break like one RSA key on the surface code using lattice surgery. And those methods were ported to also breaking elliptic curve cryptography, so the elliptic curve discrete logarithm problem. And what people find systematically is that the quantum resources required to break, say, one RSA key, like at 2000 bits, 2048 bits, is about 1,000 times more difficult than breaking one elliptic curve key at 256 bits, just because the size of the keys are smaller, it requires less gates. So it means, like in practice, that the elliptic curve cryptography will break before RSA. So the amount of quantum compute you need to break one RSA key, you break 1,000 elliptic curve crypto keys. And it's so low actually that even like at 256 bits, it's roughly the difficulty of RSA 800, which is broken classically. So like we're just missing a classical algorithm to break elliptic curve crypto. It's really that vulnerable. And over the years, that's kind of the blue curve. The estimation of the resources to break elliptic curve crypto has gone down. So we started from tens of millions, almost like 1 billion qubits, and now like there's recent methods, say from Alice and Bob, where like it's hypothesized that like down to 100,000 qubits would be sufficient to break elliptic curves in hours. There's also recent results from PsiQuantum from Daniel Litinsky, where using active volume and special techniques where he only breaks like some part of the key on quantum and the rest classically, it would be possible to break elliptic curve cryptography with only 50 million Toffoli gates, which is, I'll show later, is extremely low with respect to other quantum applications. We have very few fault-tolerant quantum applications which require as few gates as breaking elliptic curve cryptography. Same Alice and Bob, now 2 years ago, like they published like a method for their architecture, and the one of the interesting components is first like the number of physical qubits that you would need is extremely low. It's on the order of like 100,000 qubits. And you also see that even like the transition the cryptanalysis will be rather sharp because if you have like a 10,000 qubit, well, assuming like the performance of the device, like if you have 10,000 qubits, you can break 32-bit elliptic curve key, which you can do in seconds on the device you're using to watch this video. But if you scale just the machine by a factor 10, then you're already in a regime where elliptic curve at cryptographic grade keys can break, which means that if you're waiting for small keys to break, you have very little time to upgrade your systems to like a post-quantum cryptography. So the moral of that is that like we know with a fairly low number of qubits with respect to the roadmaps, it will be possible in a few years to break several hundreds to thousands of keys per year with Bitcoin, which can be a problem for cryptocurrencies. And the timelines are largely driven by the commercial roadmap. So in 2021, DARPA released like a collective roadmaps of all the quantum companies, and it was roughly established that the industry is aiming at million scale quantum computers by 2029, 2031, up to like say 2033. So like the end of the decade, and then we see it also like say on the Google roadmap where they are currently like at the stage where they did like the Willow demonstration and they're like scaling logical qubits. Same for IBM, like they want to go like to large fault-tolerant machines by the end of the decade. Everyone is kind of converging on the time scale where if it becomes possible, more or less there's a catastrophe, physical catastrophe or like radically new physics. We expect quantum computers to be able to break elliptic curve keys roughly by the end of the decade. And the issue is that there isn't much warning. Like the resource estimation for this, so this is compilation from Metric. There's also from the Unitary Fund. There's also the plot like showed by like Travis like a few weeks ago, and also done by IBM, where if you collect the applications as a function of the circuit size or the circuit width and the number of T gates, so like the difficult resources like for photon quantum computing, uh, we have very few commercially relevant applications which are as easy as Bitcoin. So like factoring is like further down the line. It's like almost 10 to 12 operations. It's wider circuits. Quantum chemistry, say FEMOCO, it's like 10 to 15 gates. So like it's already almost like 10 million Bitcoin keys in difficulty. Other than simple Fermi Hubbard models, we have very few applications other than breaking elliptic curve discrete logarithms. And that's a problem for preparation on the side of cryptocurrencies because we won't have much warning. Okay, like say there's all these chemistry applications, like all these optimization applications, like coming before um, the machines, like even the commercial machines can be a threat to cryptocurrencies. And the estimates of the experts on the side of RSA, which is 1,000 times more difficult than elliptic curve crypto, kind of matches also those timelines where a large fraction of the industry, say more than half, expects cryptographically relevant quantum computers by 15 years. Here for an algorithm which is 1,000 times more difficult than breaking elliptic curve crypto. So we can shift that line a bit to the left for the threat to cryptocurrencies. But those machines will be expensive. So like there won't be an infinite rate of cryptanalysis. So like the large quantum computers are probably going to be like a few, like at least $1 billion, like up to 10. If you can break 1,000 keys a year, then you can expect that the early cost of attacks will likely be like millions of dollars. So like every per key. So like not all keys have the same worth on cryptocurrency. So some of them are worth several $billion depending on like what's secured. Others are worth like fractions of cents. So the surface of attack and the threat level, like when you zoom in, like it depends a lot on like the specific address in the systems. And those timelines are also aligned with like NIST schedule for upgrading for sunsetting elliptic curve crypto. So the aim there is to like deprecate like weak elliptic curve crypto in 5 years and completely disallow it in 10 years. And like the disallowing by then will probably be done naturally. Like if keys don't have a lifetime of more than a few seconds in the wild, like people will just not use them at that point. Upgrading cryptocurrency. So we have large quantum computers are like on the way. We know like elliptical discrete logarithm is one of the easiest applications. Okay, a quick primer on how Bitcoin works roughly and like what is the surface of attack. So a blockchain, as the name says, it's a chain of block. So like people submit transaction to the mempool, if you want, or like the broadcast transactions. Those transactions are collected by miners. Those miners will bunch them together, then solve a mathematical problem. So they're doing proof of work. They're establishing consensus by hashing, for which they have to make sure that the hash that they get out of like a block that they created has to be smaller than some given number, which establishes the difficulty and roughly the timing of the network. And when they successfully mine the transaction, then they get some coins as part of the network, which creates an economical incentive to keep the chain going. So like it kind of mixes cryptography and incentive system, with kind of like the brilliance of the scheme. And the consensus part is relatively safe. It's really the ownership, as I was saying. Like so, when you sign transaction, you own a private key, and this is the part which is like at risk by quantum computers, and it's actually it can cripple like those systems. And here I'll like explain a bit like more the problem. So like there's different types of keys and addresses on Bitcoin, and not everything is at risk at the same time. So like the big the first major risk is like the Bitcoins of Satoshi. So Satoshi is the presumed anonymous founder of Bitcoin. Back in 2009, he mined like he was like one of the few miners. So like you see like the black lines that was the CPU there, like just mining blocks. In about a year, he mined roughly like 1 million Bitcoins spread over maybe 50,000 addresses. So in blocks about like 50-ish, 100-ish Bitcoins. And in those years, so before 2012, people were using the public key as the address. So there is a set of a few thousands of public keys tied to about 1 million Bitcoin at current price, which is close to $100 billion of bounty at the beginning of the blockchain, uh, which is just available to anyone. So you just download a copy of the ledger and you get like all those keys, and you have an infinite amount of time to break them if you have a quantum computer. And the first people to break them will literally be able to take those coins and move them to their own wallet. And then this is vulnerable, assuming Satoshi is not active anymore, or like if it's someone who passed away, then they will not move until the quantum attackers take them. And like depending on how it's done, this can create like a massive amount of volatility. It depends on the will of the attacker. There's a second set also of issues. So like after 2012, it was discovered, okay, people thought, okay, like if there's a quantum computer, like maybe it's not safe, it's not super good for privacy either to just expose the public key. So in those years, since 2012, when you create an address, you publish the hash of your public key, and you don't publish the public key until you do the transaction, which means that until you do the transaction, hash will not be broken by quantum. You're kind of safe. But from the moment you publish a transaction, if you either reuse the address, then your public key is exposed and it's as vulnerable as the early coins. And in the future, say in the mid 2030s, close to 2040s, like the time, even if you only have 10 minutes of your transaction in the collective like mempool, like if a quantum computer has tendency to break it, if it can break it, then you can still lose your money. So like even this protection will only cover some time and force people to eventually migrate. And it used to be a fairly low numbers of address reuse, but since large exchange are often reusing addresses, it means that now there's quite a large proportion of the network which is exposed, like in terms of value. It can be up to like close to 80%, which is very large. So like large addresses could be attacked. And we see it in the distribution. So like large asset holders, large exchanges, they concentrate most of the wealth of the network. Which means that there's about 2,000 addresses, which contains like 30% of like 38% of the network. So it means that if you have a quantum computer, you can break like 1,000 keys a year. You can already attack like easily like 30% of the network within a year and like just take it, which can be crippling like to the entire network. And when you start upgrading, since there's like tens of millions of addresses, the network can only support 7 transactions per second. It means that when people upgrade to new wallets, like they all have to do it sequentially, like 7 people per second. So assuming they all do it at the same time, it will take months just to process all the transactions. In practice, it's probably going to be years with only a fraction of it upgraded. So it's actually a difficult coordination challenge to upgrade blockchains. There are starting to be solutions to implement like the post-quantum cryptography, notably the schemes introduced standardized by NIST this year, and like the ones which will be standardized in coming rounds. The BIP 360, so BIP is a Bitcoin improvement proposal, which was introduced by Surmount Systems, where they define new types of addresses which are quantum resistant, but will require a hard fork to introduce the verification method, which has not been done yet, and requires like a coordination like effort. And there's also like a more like a bit more brute force method, so BIP 347, which reintroduced an operation which existed like years ago in 2010, which would allow for like the creation of the Lamport vault directly on the blockchain. So like it's not a standardized method, but it's known to be quantum secure, at least as secure as the mining itself, like as the mining function itself. But introducing like one of the open problems which have not people haven't started to tackle yet is like the introduction of post-quantum cryptography on Bitcoin will likely require an upgrade of the block size because the blocks were meant to contain transactions signed by elliptic curve signature, which are rather small. If we increase the size of the signatures by a factor of a few hundreds, then to keep the capacity of the network will likely require other changes which require like more consensus on the network, which is not that easy. And that's the stage where we're at now. So like a year ago, there were no such Bitcoin improvement proposal. Now those have been proposed. In the next few months, I hope to see like at least one adopted, such that we can start the migration to quantum like resistant cryptocurrencies, like to post-quantum cryptography on cryptocurrencies. And yeah, so if there's a message is that like quantum computers fault-tolerant quantum computers will likely have a very strong impact on cryptocurrencies early on, like in the development of the technologies. And if we don't want massive volatilities, especially now that those assets are flowing into retirement funds, like through like financial instruments, it's time to start upgrading blockchains now. So thank you.
Wonderful.
Okay.
Thank you so much, Pierre-Luc. This is wonderful and very, very, very informative. We have several questions in the Q&A, and for those who haven't submitted in, please push the button at the bottom and submit in your questions. There are two questions on ECC. So let me start off with, could you repeat your comment about ECC being broken before RSA? The understanding was ECC 256-bit key is on the order of an RSA 3072, but if you could just give a little clarification for that one.
It is true classically. So classically, it is like the degree of security of ECC. If you use like the polar row, like if you count the classical operation to break ECC 256, it's roughly the same number of operations as breaking RSA 3072 bits. Quantum is the opposite. So, and it's to me, it's a mystery why, but no, I understand why it's easier classic like quantumly, but I don't understand why it. Are we missing an algorithm classically? Because with Shor algorithm, the main determinant of the difficulty is roughly the key size. So like the implementations of the group operations are such that if you count the numbers, you end up with a compilation which requires about 1,000 times this gates. So like it's a very mechanical calculation. And it has been known since about 2003, since the first paper of Cruz and Zalka, that ECC would be easier to break than factoring. People are doing numbers and they still see the same phenomenon. To me, the real mystery is, are we missing a classical algorithm for ECCs? Because I would expect the quantum complexity to be the same as the classical one. So, yeah, so that's my observation.
Oh, that's fascinating. And I guess on the ECC question again, of the implementation, are you looking at some ECC areas where they can maybe look as early signals for broader vulnerabilities, maybe for Internet of Things and devices like that? Is there any way to kind of look at these and any potential mitigation factors that folks should consider?
It will have to be mitigated. So Internet of Things also is tricky because there's going to be hardware deployed, so you will likely have to upgrade the hardware which is like out there in the field. Like where ECC is also used is like on TLS and shakes like on the internet, but like this has started to be upgraded. So I know like Google Chrome started to use some amount of PQCs, like it's already fairly deployed. Cloudflare is reporting already like I think 30% of internet traffic, which is signed by lattice methods. those are vulnerable, like, but being more centralized in the sense they're, well, the centralized part is easier to upgrade. For IoT, the fact that you have to upgrade hardware is a daunting task. But again, like it's done by a centralized, if it's done by a central company, then at least you know where the stuff is, you can upgrade it. In the case of Bitcoin, you have to take every people individually will have to move their stuff. So like it's like all the customers have to be mobilized in that case.
Okay. I guess the upgrading question relates to something that was submitted in the Q&A, which is sort of as quantum computers, as you had mentioned, there's no kind of gate model quantum computer that can break encryption today, but there are growing quantum computing systems that are happening. So as the vulnerabilities occur, are you going to see kind of this race of having to continually upgrade your blockchain as quantum systems get bigger? Is it kind of a one and done, or is this going to be a race between the two of you upgrade and then keep moving?
We hope not. So to me the big wildcard. Okay, so the hash-based method I would consider probably unless there's the mathematical revolution, I would consider hash-based method probably safe for like decades, if not centuries. So that part wouldn't need to be upgraded. The more recent schemes, they're heavily studied. There's a lot of people who looked at them, but there are more structure and more mathematical assumptions. So we don't know for sure like how long they will last. So it can be like years, decades, it can be centuries. We don't know. There's the wild card that we're gonna get very, very strong AI in the next decades, which could lead to like a mathematical attack on those systems, which we have not thought like already. So my advice on that is like for the keep the mind open and like aim at having upgrades as crypto agile as possible, because we may end up in the situation where we have to re-upgrade those schemes in 10 years. And we just don't know at this point. Like there's a difficult to predict like the future 20 years from now at this point with everything
Absolutely.
evolving at the same time. Yeah.
No, absolutely. There is a question here about elaboration on the Litinsky work, about kind of the active volume approaches allowing for simplification of quantum resources required and the degree to which there might be additional improvements at an algorithm architecture level. Could you give a little bit more of an elaboration on that point?
Yeah, but I would say the general trend is that okay, the first resource estimation they assume like the nice flat surface code, like infinite nice surface code. It's not really like what's going to be built. Like a Litinsky approach with active volume, like modulates the amount of error correction given by different components for like the entirety of the algorithm. And he also introduces like a few optimization where the like you can stop the algorithm. It happens to be like that. You can stop the algorithm like almost midway and do some part classically and the other part like on the quantum computer, like a large part. With a bunch of optimizations which were introduced, what the general trend that we're seeing is that most of the old estimates, they always end up being upper bounds. And each time we find better optimization, or like we specifically optimize the algorithm, say for the specific curve of Bitcoin, we just keep reducing the resources required to break those. And essentially, the phenomenon that we have been observing is that the dates, like where the two lines intersect, only keeps getting closer to us instead of like going the other way. And Litinsky is really like is a data point in that trend. And like he introduced several interesting optimization, which has not been ported to the surface code yet or other architecture. So like we may even see like further progress.
Oh, that's fascinating. I know we're coming up on time, so I have one quick question
Yeah.
at the end. I know you talked about hashing, and I guess the question is, will quantum ever break hashing?
I would not count on it in the next 50 years. Like the numbers okay, we would need a very different approach to it. If it's only Grover, you would need like a quantum computer, probably the size of a small astronomical body to try to attack Grover. Like just the number of operations, if you work it out, like 10 to the 40, which is like in those chart of like applications, like in the other room, like it's way out
So,
there in
so definitely
the
not
size.
anytime soon in any way.
No, no,
Okay.
no. Or maybe in between, but it's still a lot more difficult than breaking keys. Like the keys are really the priority.
Thank you so much. We are at time. For those of you who asked questions, we didn't get a chance to them. We will collect those and provide them to Pierre-Luc so he can answer them offline. Pierre-Luc, thank you so much for your time today. We really do appreciate it. This has
Thank you for the
been
invitation.
truly fascinating. And thank you all. And I wish everybody a happy new year and look forward to the International Year of Quantum, which is 2025.
Good start.
Bye-bye, everybody.